Alright, so in today's lesson we're going to be talking about the chain rule. And this is a really important derivative rule. It's not a basic rule. So it builds on some of the things that we've learned in the past. And an important definition for us today is a composite function. This is a function within a function. So for example, say you have, I don't know, sine of x squared. This is considered a composite function because x squared is in the place where we would normally just have x. So you might say that f of x is sine of x, g of x is x squared, and this up here, well, it's f of g of x. So you might remember composite functions from Algebra 2. But basically, you take two functions and you put one inside the other. And that's what we're going to be finding the derivative of today. So we'll be determining how to find the derivative of such a thing. So if you flip over, there's two ways that you can word the rule. And we're just going to go ahead and write them down at the top here where you should have cut off a piece. And the first way is dy over dx, which we know means the derivative. So the derivative of y with respect to x is dy over du times du over dx. And we'll talk about what that really means here in a little bit, but the u in there stands for u substitution. So we're going to be using a substitution to help us do the derivative. Another way you can think of it is that the derivative of a function f of g of x is equal to f prime of g of x times g prime of x. So both of those right now probably don't mean a whole lot to you, but hopefully they will here as we go through our foldables. So first of all, let's talk about the decomposition of a composite function. So basically, developing an eye for what the two original functions were before they were composed. So if you open up, on the left side, we're going to talk about the types of problems we used to do and the ones now. So without the chain rule, these are the type of problems that we would have done. Like y equals x squared plus 1, we could find the derivative of that. Or f of x equals sine of x. Or y equals 3x plus 2. Or f of x equals x plus tangent x. All of these things we could have found the derivative of without the chain rule. But here's some things that there's no way you could have done it otherwise. So with the chain rule. And try to notice the difference here. Say we wanted to find the derivative of the square root of x squared plus 1. You can see that this went under a radical and now it's no longer divisible. Derivable. We could have done sine of x, but we can't do the derivative of sine of 6x. We just don't know how. We could have done 3x plus 2, but we can't do the derivative of 3x plus 2 to the 5th power unless we double distributed it all out, which would be a big mess. And then lastly, we also could not do the derivative of x plus tangent of x squared. So you see the subtle difference here in all of these problems is that you've got a function within a function. You have composite functions going on, and that's what's causing the problem. So to actually decompose a function, we have to start with our composite. So say we have y equals f of g of x. That just means you've got a function that is composite. So for example, Say we have y equals 1 over x plus 1. Well, we have to be able to pick out the inside function, g of x, and we're now going to start calling that u. So what function is inside of the other function here? Hopefully you notice that it's this x plus 1. Normally it's just x down there if you think about an original function. So we're going to call u x plus 1. And then our y then, we're going to call f of u. So we're going to change it to be a function with respect to our inside function. And that would be y equals 1 over u. So you can kind of see, here's our inside function. Now we're calling it u. And so this is where I get the word u substitution. Because now we can do the derivative of this really easily. We'll talk about actually doing it here in a moment. But let's do a couple more decompositions, pulling it apart. So say we have y equals sine of 2x. So what is our inside function that's causing this to be composite? Hopefully you thought 2x, because that is the inside function. So I'm going to write it right here. So now my u equals 2x. This allows me to do a u substitution and say that y is now simply sine of u. Okay, let's do one more. Say we have y equals tangent squared x. This one's a bit trickier, so you have to figure out what is our inside function. Before it was composed, what was the inside function? This one is actually tangent x. So our u is tangent x because it's what's being squared. And our original function was y equals u squared. So we're decomposing it, and we could compose it once again. If we wanted to, we would just substitute x plus 1 back in for our u. Alright, so in the next video we're going to talk about actually using the chain rule. We've set the foundation, now we're going to use these rules.